Okay, let's have a look at this paper, which was produced for 2021 series. But of course, there were no exams sat during 2021. So on to question 1. This question takes material mostly from Unit 1 in the topic acids, bases and salts. In this question, the sodium hydroxide solution is being added to a solution of hydrochloric acid. So the concentrations are both the same. It's a 1 molar solution in each case. The hydrochloric acid is in excess. So the first question is, write a balanced simple equation for the reaction between sodium hydroxide and hydrochloric acid, and then include state symbols. Well, sodium hydroxide is just NaOH. Hydrochloric acid is HCl. Now, as this is an acid and base, or acid and alkali reaction, it will produce a salt and water. So the salt in this case is sodium chloride. That's the salt, and then water is formed. Remember, the surname, if you like, of the salt comes from the acids. Hydrochloric acid always produces chlorides. And the first part of the salt here is usually a metal ion, so it's sodium in this case. On to part 2. So explain using evidence from the method whether this reaction is exothermic or endothermic. Remember, exothermic is where the temperature increases, and endothermic is where it decreases. So let's look up at the method. And I'm going to look at this introduction, which you can see here. And it says the mixture was stirred using a thermometer, and the highest temperature reached was recorded. So that means that the temperature is increasing, which means it's exothermic. On to B part 1. Explain why a polystyrene cup was used instead of a glass beaker. Well, this experiment involves heat being released, and that is what is being recorded, the highest temperature that's reached. So we want as much of that heat as possible to be contained within the cup. And polystyrene is just a better insulator than glass. I suppose you could say that the polystyrene cup is a poor conductor of heat. Part 2. Explain why the solution was stirred after adding the acid. Now, I've put the method to the side. Hopefully you can make that out. So you can see here that the hydrochloric acid was added, and then the mixture was stirred using a thermometer. The highest temperature reached was recorded. Well, the reason why we would stir that mixture is just to make sure that the reactants are thoroughly mixed. Or you could say it's to ensure that there's a uniform temperature. Part 3, state and explain one improvement which could be made. Well, I've already mentioned about the need for heat to be trapped inside, and you can see from the diagram that heat can just escape through the top. So an improvement to this experiment would be to use a lid, and that would help to prevent heat loss. Now, another improvement you could make is to put the polystyrene cup inside a glass beaker. In fact, that's what we would often do. Now, that also helps insulate it, because not only do you have the polystyrene cup, but then you have the glass beaker, and there's a layer of air around it. So that improves insulation, but it also helps stabilize the apparatus. If the polystyrene cup is on its own and you have this thermometer, if the thermometer lies up against the side of the polystyrene cup, it can easily topple over. So for stability, what we would often do is just place it inside this beaker. On to part 4. So how could you ensure that the investigation is a fair test? Well, from the method, it was originally carried out with sodium hydroxide and hydrochloric acid, and then the reaction of sodium hydroxide solution with propanoic acid was investigated. So the acid was changed in the two experiments. Well, if we want to be able to compare the two, the concentrations of the acid and the alkali have to be kept the same, as well as the volumes. C. Calculate the number of moles of sodium hydroxide that were in the cup at the start of the experiment. Well, number of moles equals concentration times volume. The concentration of the sodium hydroxide solution is 1 moles per cubic decimeter, and times that by the volume, which is 25 cubic centimeters. As it's cubic centimeters, I need to change that into cubic decimeters, so divide it by 1,000, and I get the answer of 0.025. D part 1. Explain why the temperature change for the reaction between the hydroxide solution with propanoic acid was less than the temperature change when the hydroxide solution was used with hydrochloric acid. Well, propanoic acid is a weak acid, and hydrochloric acid is a strong acid. That's the only difference that is involved here. And the weak acid will therefore produce a smaller temperature rise. Now make sure you comment on both acids, because both acids are mentioned in the question. You've got to refer to both of them. Part 2, this is the word equation. Part 3, an ionic equation for neutralization. Now, it does not matter what the acid and alkali are. So this could have been sodium hydroxide and hydrochloric acid. It could have been sodium hydroxide and sulfuric acid. But here it's propanoic acid and sodium hydroxide. The equation for neutralization, or the ionic equation for neutralization, is always the same. H plus comes from the acid. The hydroxide is the OH minus, and when those two react, it forms water, which is just H2O. No state symbols are required here. It doesn't mention it in the equation. But if it had asked you for state symbols, then this would have been AQ, AQ, and L. So remember, if you see this here, the ionic equation for neutralization, this is the equation you always put. Question 2 is about the conductivity of a number of samples. So the results are down here, and then the question follows. State and explain the electrical conductivity of each substance using the results. So first of all, I'll state the electrical conductivity of each substance. So graphite and titanium are good conductors because the bulb lights. And make sure you put in electricity. Don't just say that graphite and titanium conduct. And then you can see that the sulfur, sodium chloride, and iodine do not conduct electricity. Now we can move on to explaining the conductivity patterns. Well, graphite and titanium have delocalized electrons that can move and carry charge. The sulfur and iodine don't have any delocalized electrons. Now, the sodium chloride, it's ionic. And ionic substances, when they conduct, which is in the molten state or in the liquid state, they conduct due to the movement of ions. It's not electrons. And because it does not conduct, it means that the ions are fixed. They cannot move. Question 3. Again, this will be taken from acid, bases and salts topic in Unit 1. So balance simple equation for the reaction of the hydrochloric acid with copper to carbonate. Which is there. The copper to carbonate is green. The copper chloride solution, which is formed here, is blue. Copper solutions are usually blue. Okay, on to part B. Describe, given experimental details, how you prepare a sample of pure, dried, hydrated crystals. Okay, so the method then of making this salt is something similar to the following. So I'm going to add hydrochloric acid. We need 25 cubic centimeters of hydrochloric acid. Now, if you're not told what volume to use, you could use 30 or maybe up to 50 cubic centimeters. But we're told 25. We're going to measure that out using a measuring cylinder. And I know a measuring cylinder is fine here because it's just 25. If it had have said 25.0, then a pipette or a burette would have to have been used. But the fact it just says 25 means that it's a measuring cylinder. Okay, I'm going to place this into a container, and a beaker is fine, or it could be a conical flask. Now we want to make sure that that acid is all used up. So the copper 2 carbonated is added in excess. You're told that up here. Excess is added. So at this stage, that excess copper 2 carbonate is going to remain unreacted in the beaker. So you can see with my good drawing, we've got our copper 2 chloride solution, which is turning blue. The copper 2 carbonate is green, and when it stops reacting, it will remain in the solution. So this copper 2 carbonate now in excess needs to be removed. So this mixture is now filtered, and the excess carbonate gets trapped in the filter paper. Your clear blue solution of your copper 2 chloride will now be in the evaporating basin. Now there's too much liquid in here, so what has to be done is that some of this liquid has to be evaporated, and we usually do that to about half its original volume. And once the volume goes down to half, so now the diagram just shows that it's about half its original volume, the remaining liquid is allowed to evaporate slowly, and in that way crystals will form. So we allow it to cool and crystallize. If you heat the original solution to dryness, in other words, you just keep heating it until all of that liquid has evaporated, you won't get crystals, because you'll drive out the water of crystallization, and you'll end up just with a solid or with a powder. So that's why the remaining bit has to evaporate slowly. Let's look at what the question is asking us to do. How do you prepare a pure, dry sample? So now these crystals have to be dried off. Now you can simply filter off those crystals, because there might be a bit of liquid remaining, and then dry between pieces of filter paper. Don't say paper towels, because bits of the paper towel can come off onto the crystal, and it has to be more than one piece. So again, here I've indicated pieces, so that's more than one. So don't say dry between a piece of filter paper. You could also just use a low temperature oven or a desiccator. In the case of the oven, it has to be a low temperature. If it's high, then the high temperature can drive out the water for crystallization, and you would end up with not having crystals. Okay, part C. Describe how a flame test is carried out to prove that it contains copper 2 ions. Okay, I'm going to use a nichrome wire, which is dipped in concentrated hydrochloric acid. That's going to be placed into the sample and then into a blue Bunsen flame. And if it contains copper 2 ions, the flame will be a blue-green colour. And both those colours are required. A few drops of silver nitrate solution are added. State what would be observed. Well, chlorides react with the silver nitrate, and in particular react with the silver ions to form a white precipitate of silver chloride. Now the equation for that, you're not asked for it here, but it would be Ag plus, this is an ionic equation, plus Cl minus, and that goes to give AgCl, which is your white precipitate. So this is your solid, and then the silver ions, they're dissolved in solutions, they're aqueous, and the same is true for the chloride ions, they're in solution. Anyway, what would be observed? White precipitate or white solid. Remember, a precipitate is just a solid that forms on mixing two solutions. On to the next question then. So here, calcium is reacting with hydrochloric acid. The gas, which is hydrogen, has then been collected over water. So part 1, suggest one error which may occur in this method. Now, let's read what it says up at the top. To start the experiment, calcium is dropped into the flask and the stopper quickly replaced. So the acid is in here to start with. And then if you imagine, the calcium is tipped in here and then the stopper is replaced. So some gas could have escaped before the stopper is replaced. And so that's a source of error. Then part 2, the labels A, B and C are, well, A is a conical flask, B is a delivery tube, and C is a water trough. A basin would also be fine there instead of a water trough. B then, calculate the volume of hydrogen gas produced. And it has to be in cubic centimetres. And explain whether 50 or 100 gas syringe would be most suitable. Okay, well, we've got 1 gram of calcium. So what we've got to do is work out the number of moles of calcium. Now we can see that the calcium and the hydrogen are in a ratio of 1 to 1. So that means that the moles of hydrogen produced will also be 0.0025. This now needs to be converted to a volume, and when you're using or dealing with volume, we use 24 cubic decimeters or 24,000 cubic centimeters. So the question here wants the answer in cubic centimeters. So remember, number of moles equals volume divided by 24 cubic decimeters or 24,000 cubic centimeters. So we're after this. So the volume of hydrogen will be then 0.0025 times 24,000. And that equals 60 cubic centimeters. Now, the other part of the question is asking us to explain whether a 50 or 100 cubic centimeters gas syringe is most suitable. Well, obviously, if it was 50, that's not going to be able to hold the 60. So it has to be a 100 cubic centimeter syringe. See part 1. This has to do with the preparation of oxygen. So name the catalyst used in the preparation of oxygen from hydrogen peroxide. Well, that's manganese 4 oxide. Or you could say manganese dioxide. But don't say something like manganese oxide or manganese 4 dioxide. Okay, so it's just one of these two possible answers. And that catalyst is black. Part 2, describe the appearance of the hydrogen peroxide. It's a colourless solution, or liquid is fine. Now don't say clear. It is clear, but the colour of it is colourless. Remember, you can't use clear to describe a colour. Clear just means you can see through it. And then the test for oxygen gas is that a glowing splint relights. Question 5. So here we've got a number of chemicals, so P through to T, and different tests. So we've got to identify each one. So let's start with P. It changes from orange to green when warmed with ethanol. Well, this is an alcohol, and the chemical that changes from orange to green when it's warmed with an alcohol is acidified potassium dichromate. There's one mark for acidified, one mark for the potassium dichromate. And the ethanol would get oxidized into its corresponding carboxylic acid. On to B. Q changes from colourless to milky when carbon dioxide is bubbled through it. Okay, well that has to be lime water. Or you could say calcium hydroxide solution, which is the chemical name for lime water. On to R. R changes from orange to colourless when ethene gas is bubbled through it. So ethene is an alkene, and the test for alkenes is to use bromine water. And bromine water is orange, and it goes from orange to colourless. S. White fumes are produced when a glass rod is dipped and applied to a sample of ammonia gas. Okay, well the test for ammonia gas is to dip a glass rod into concentrated hydrochloric acid, and then when the two fumes mix, you get this white solid or white fumes of ammonium chloride. So S has to be concentrated hydrochloric acid. Finally, T. T changes from colourless to pink when added to sodium hydroxide solution. Again, the only chemical that you've come across that would change from colourless to pink would be an indicator, that is phenolphthalein. So remember, it's colourless to start with and when it's an acid, and then it goes pink in alkaline solutions. And hopefully you're still here and made it to the final question. Complete the table below. The colour of the hydrated sodium carbonate, it's white. And we'll know that because sodium is in group 1, and remember, compounds of group 1 or white solids. And when they dissolve in water, they form colourless solutions. So that's just the general rule. If this had been potassium carbonate, it's also white. Again, if this had been sodium or potassium carbonate solution, this would have been colourless. The same applies to group 2 as well. Any compounds of group 2 that are solid or white, and if they dissolve in water, they'll form colourless solutions. Okay, on to part B. What piece of apparatus is used to measure 25.0? Now, we had a question similar to this a bit earlier. Remember, if it's just 25, then it's a measuring cylinder. But because it's 0.0, that means that a pipette is used. Or you could use a burette as well, I suppose. Part C then is draw a labelled diagram of the assembled apparatus to carry out the titration. So let's just make sure we're getting things the right way round. 25 cubic centimetres of the solution, which is the sodium carbonate solution, is placed in a conical flask. And then it's titrated against the acid. The acid goes into the burette. So let's see if we can draw this. So there's the burette with the acid in it. Make sure that everything is labelled. And underneath that, I'm going to have the conical flask. Again, I've just shown that the sodium carbonate solution is in there. You could have this on a white tile as well. And don't forget that in the solution, you also have your indicator, which in this case is methyl orange. On to D, calculate the concentration of the sodium carbonate solution. So the information is shown here over to the right. And we need to start with the reactant that has two values already attached to it. So you can see here that the concentration of the acid was 0.1 and the volume of the acid was 24.5. So here we've got our two values. So we can work out the moles of the acid, and from that then we can work out moles of the sodium carbonate solution. Remember, number of moles equals concentration times volume. And keep that as 0.00245 to 3 significant figures. Don't round moles too much. Okay, certainly don't be doing it to one significant figure, and 3 is good practice. Okay, we can see then that the ratio of acid to the carbonate is 2 to 1. Therefore, they're going to be half the number of moles of sodium carbonate. I can then rearrange the equation to give concentration, which is moles, 0.0012225 over the volume. So the volume in the conical flask was 25. And then I'm going to times that by 1,000. And that gives a value of 0.049. If you don't like working with this value here, then just convert the 25 into cubic decimeters to start with. So you could just do 0.0012225 divided by 0.025. And I say it just does away then with this 1,000 in the equation. On to E, calculate the value of X. Okay, so we've got the mass of the sodium carbonate, which is up here, 7.84 grams. And we know that the concentration is 0.049 moles per cubic decimeter. So 0.049 moles has been produced from this 7.84 grams. So if you remember back to, well, you did this in Unit 2 and also in Unit 1, but the number of moles equals the mass over the RFM, or MR. So we can simply rearrange this equation to give us the MR. So well, I'm just going to stick with RFM here. That's going to be 7.84 divided by the number of moles that produced, which we worked out in part D, which is 0.049. And that equals 160. So just be aware that very often in titration type calculations, an answer to one part is often carried through into the next part. Anyway, so we now know that this whole thing has a mass of 160. Now you can work out the mass of this. The Na2CO3 has a mass of 106. So that means that the difference between these two must be due to the X water. So 160 minus 106 equals 54. That 54 is caused by water. Water has an MR or RFM of 18. So 54 divided by 18 equals 3. So that's what X is. And final question, an alternative practical method to determine X. You did this in Unit 1, and that's where you heated your hydrated salt to constant mass. You used an evaporating basin or a crucible.